Okay, I hope I'm audible. So let's start. So till now we have discussed basics, overall view of overall architecture of neural network, neural network. So we know what we are trying to do. We are trying to can say we are trying to draw a line. We have a lot of data points. Say for example, two-dimensional. A lot of data points are there, and here something. So we are trying to separate this data point using a single line. Here it is two dimensional, so I need a line to separate them, right? So I'll start a line which is best option, something like this, a line. Okay, although a lot of options. So this line equation we are trying to model, which is maybe p1 parameter 1 into w1 parameter 2 into w2 plus a constant b equal to 0, something like this, right? So neural network is trying to get the solution. What is the line? What is the equation of this line? So how is it going to reach the conclusion? Now it is going to get to this line by the process called learning or training. Learning or training or learning. Okay, this is what the neural network is trying to do. Now, how the training happens? Because we have to train using some already existing data, right? So we need to tell the neural network this is already existing data, and this is a girl. For example, we have girl and boy. Say we have to tell the neural network, say in this characteristics where the people like shopping, this is a girl, and this is another girl, and they also have some liking for trekking, which is very less. So all these people who are having less interest in trekking, maximum interest in shopping, can be girl. So we are training this. So neural network is trying to understand. Okay, all these data points here is going to be girl. So on this area is more probably going to be girl. And likewise, high interest in trekking, low interest in shopping is going to be a boy. So it's like this. It can be complicated, but based on the data, based on the input data, the neural network is trained or it is learned. So what is learning actually? It is nothing but you're manipulating the weights W1 and W2 and the bias also. Like so, it's changing bias. We can say this line is positioned in different parallel positions. Changing. Okay. So that's about training. So today we'll be discussing the training part, training and learning part. Okay. So how can we define training or learning? So we can say training or learning is minimization. Something minimal. Let's discuss what is minimization later. We can say training or learning. Training or learning. Learning is minimizing loss or error function or cost function. It's called is minimizing. There's a minimization. There's a new term I think. Minimization. Minimization of loss, cost, or error. These are all the used function. Okay, these things are all used in literature. Loss function, cost function, error function, or something. It also called objective function. Objective function, right? Minimization of something. Loss function, cost function, or objective function, right? So what is all this about? What is called minimization? What is minimization? We are trying to find the best solution. So minimization. Also, sometimes you may heard of maximization. Maximization. So as the name, as the meaning states, in one case we are trying to find the maximum. Maximum. This is called maximization. So we have a lot of options. This is two-dimensional plane. Option 1, 2, 3, 4. We have different options. So the maximum best option is here with respect to maximization. When I'm thinking of maximization, this is the best. When I'm thinking of minimization, maybe this is the best. This is minimum. This is minimum. And this is maximum. Okay, so your problem will give you idea. We are trying to maximize, you're trying to minimize. For example, you always try to minimize the cost, right? So cost we always try to minimum, because whenever you buy something, a lot of money or a lot of budget, so you try to minimize the cost of the thing. Or but for example, what you try to maximize, you try to maximize the efficiency. You're trying to buy a car, so you'll find a car whose maybe this engine is most efficient or economic. So maximize the mileage. For example, mileage you have to maximize. Mileage you have to maximize. Same time, consumption, energy consumption, you have fuel consumption you have to minimize. So it depends on the problem. So the problem will tell you whether you have to minimize or maximize. But when you think of cost function, error or objective function, you will always try to minimize it, minimize the loss, right? Because any system or any model which had a less error. So okay, so we always try to minimize the lost cost error function, but maximization problems are also the okay. So that's it. Okay, so now we already discussed what is learning or training. It is minimizing loss function, cost function, error function, whatever. We are trying to achieve the best fit, best line. Okay, so now the question is how to evaluate. How to evaluate, which is my how to evaluate. How to evaluate, which is my maximum point, which is a minimum point, etc. Now, so we'll come back to our earlier example of boys and girls. So we have, say, something. You have the axis, or one axis I'm drawing shopping, and that is, say, trucking or gaming, whatever. Okay. So in this example, we have different points. You can say different girls. Girls I call G, 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 and boys are in different color. And boys are also the who doesn't like shopping at all. Boys, they like trucking. Okay, so these are the points which we discussed in the early classes. Now, now initially, your neural network is totally untrained. It doesn't have any learning, so it doesn't know the solution. So it will be a random line something. So here, our solution is what? Our solution is something a line like this. This is our line. Solution we know it should be something line which is just dividing the girls and boys perfectly, right? But initially, before training or learning, a neural network may not know what is solution. So initially, it might have some random weights. It may have random values of W1, W2, or it can start with W1 and W2 as zero initialization. So sometimes initially it may have some value like this. Say something like this, right? Where it may tell you all the values, the top are girls, right? And all the values in the bottom, maybe because initially it doesn't have any knowledge. So it will say all the values in the top are girls, all the values in the bottom are boys. So you can see here, is it right or not? No, it is totally wrong, because here all the points B are coming the top of the line, top of the line. So in the top of line, the neural network is saying it is girls, but wrong. But all those points are misclassified. At the same time, we can see girls. All the girls are also appearing in that region where my neural network or my line is saying are boys area. But these girls are all appearing in the boys area. So total misclassification is happening. So error. I should have an error. I should know that there is an error here. So I should improve this stage, because all the you can, if you have any question or something, you can unmute and tell me, because I'll not be able to see the chat right now. Okay, so here you can see the neural network is telling girls at the top and boys at the bottom, and it is wrong actually, because it doesn't have any training right now. Now how can we quantify the error? So we see that there is only one area or we can say there is only one point the neural network is classifying correctly, that is girl. That means one point is correct. First of all, things are wrong. All the points are wrong. 1, 2, 3, 4, 5, 6 wrong in girl section. Boys, all things are wrong. All the classification are wrong. 5 plus 3, 8. So we should have a tabulation. For example, how many correct options are there? You have to correctly classified only one point. How many wrong classifications are there? Tests wrongly classified 6 plus 8, 6 plus 8, 14 points. That means you have uh, only one correct answer. So we need a function. We need to quantify it. So what we'll do? We'll now design an error function. We need the error function. So based on the error function, we know that whether the neural network is perfectly classifying or there is some further improvement, right? So this error function will give us what? This give us error in mathematical terms or numerical value error. Now this error we'll trying to minimize. So here, the wrong classifications are 14. So I can say error is 14. Error is 14. So I have to reduce the error from 14 to 0, right? So I call this a minimization problem. Minimize, minimization. Okay, minimization. So what are you minimizing? You're minimizing error. So how you are getting error? That we need some equation. Now how we are going to quantify this classification? So one simple way I'm going to write here is, say for example, there is maybe some way like this. I can write like this. For example, error equation. This is error equal to sum of all individual classifications. Say if I there are n different points. For example, n, how much points are here? 15 points are there. So I equal to 1 to 15. So each of this point I'm checking whether this is correctly classified or not. So I'll first my output target. I have some target because I know this is girl or boy in training phase. We are talking about learning or training phase. Minus output from your neural network, out from your neural network or classification of the neural network. This is your error equation. So what is the meaning of this error equation? That means from each point, I'm comparing the output with the target. That is output of the neural network is this is output of neural network. Output I. This is the output of neural network. Out O. And it is subtracted from the target T. What do you mean by target? Target we know in the training phase, we already know this is a girl, this is a boy, all those output we already know. So I'll compare or I'll take the difference of the target and output of my neural network. And this I do to all the points and I add all those things. Sigma, this adding all those correct answers. That is what I have done here. All the wrong answers I added up, I got 14. And all the right answers I added up, I got 1. Now this I can put in this equation. What will happen here? From each point, target maybe, say for example, boys target is 1, because boys I represent 1, girls represent 0. So in each of these cases, I know I'm getting 1 or 0. If it is right classification, target is boy, output is boy, so 1 minus 1 0. That means that particular point is 0. That means there is no error. If the target is a boy and classification is a girl, so 1 minus 0. So there is an error in that classification. And if the target is a girl and classification is a boy, 0 minus 1. Mode 0 minus 1 is 1 again. Again, if the classification is a girl and the class and neural network output is again girl, then I'll get a 0 output. Getting? So T stands for target, O stands for output of our neural network. Getting? So each target is already defined. We already have the data. This number of people are girls, this number of boys. Individually, we have the target. Now, initially, we don't have the perfect output of the neural network. So we compare the output of the neural network with the target, whether my neural network is getting the correct answer. If it is right answer, your difference is becoming 0. So your error function at each individual point becomes 0 if it is correctly classified. If it is misclassification, you'll get a 1. 1 minus 0 or 0 minus 1 will get a high. So all those points will be added together using the sigma, and we'll get an error function. Here the error function is 14. Why? Because there are 15 points, only 1 point was perfectly classified. So I'll get only 1 point. If all the points were misclassified, the error will be 15. If these points are also misclassified, the error will be 15 because I have 15 points here. Right, 6 plus 7 plus 7 plus 8, yeah, 15 points here. Okay, so this is my error function. So my error function is E equal to sigma, going from one point to all points. So I can call it N. If N is the number of data points you are using for training. Now the target Ti minus output of your neural mode, right? Taking mode. I have to take mode, else what happens? If the target is 1, for example, the target is 1, that means it is a boy, supposed to be boy, and you're doing classing as a girl, that means there's error. Yeah, so this becomes 1, just added on later. And if the target is a girl and your letter is classing as a boy, it is 0 minus 1. If I don't take a mode, if I don't take a mode, it becomes minus 1. Although it is an error, although error 1 it's an error, but minus 1 means your previous error and this error will classify. So what I'll do, I should take a mode. So whenever there's an error, I need the magnitude, that means 1. So here also is plus 1, this is plus 1. Whenever there's error, plus 1. Here also error. So all this can be added up using a sigma, like 2. Okay, so I need a mode. So that sign of the error doesn't matter. I need to add up the error. Okay, so this is error function, or can also call loss function or cost function. So that's it. So ideally, so the problem, we can generalize the problem. We can generalize the problem. What neural network is doing, finding an optimal value, finding an optimal value for what? Finding an optimal value for W, vector W. That means W1, W2, B. Find optimal value for W1, W2, B. So that to minimize, in order to minimize the error, minimize the error. Okay, so that's it. That's what we are trying to do. Okay, so what we are trying, so we know there's a term called minimization. There's a minimization present here. We are trying to minimize the error. So whenever we are trying to maximize or minimize, we call that is we are trying to optimize. So here we are trying to optimize what? We are trying to optimize the W vector, that is W1, W2, B. Right? So whenever we are trying to optimize something, the problem changes into optimization problem. Optimization problem. So we'll discuss a bit about the optimization problem, right? So what is optimization problem? We are trying to find the best values of W and W2 so that we are trying to reduce the error. So that is kind of optimizing the error. So we are trying to minimizing the error. So that's optimization problems. So we are finding the best ways for weights, best values of the weights of the neural network and biases also. At the same time, while reducing the error or minimizing the error based on the error function. Okay, so how to do the optimization problems? For doing optimization problems, you need optimization algorithms. For optimization problems, you need optimization algorithms. So there is another field, also a new topic also, but here also we will be applying these optimization algorithms, right? Fine. Now, I just want to give you some basics of optimization algorithm. Say, for example, we'll take an example of a robot. Say, for example, we have robot. Yeah. So, what is robot trying to do? It is trying to reach a destination. Maybe it is trying to reach a destination. For example, human being. For example, there is a food here. So this is a destination. This is a destination which the human beings want to reach. But robot also is trying to find the human beings how will move. He will move left, right, left, right. You may smell it. You may get indication of someone else. But a robot also will trying to reduce the distance. What are you trying to reduce the distance? Here we are trying to reduce the distance between the food and the robot. So there is an optimization problem. We are trying to reduce, minimization the distance. So when you apply machine learning here, so the robot may have some intelligence. Maybe it may have some radiation or some light rays emitting, and based on the reflected light ray, it can get some information between the distance. So it always try to move to a direction it minimizes the distance. There are two options, multiple options are there, but it never takes a turn which is increasing your distance, that is maximizing distance. You always try to minimize the distance. So this is also an optimization problem. Here the function or the cost is distance, or loss function distance. So we are trying to reduce the distance. Okay. So in machine learning problem, we should have some ideas like radiation and something. What the robot does, it tries to move a bit here and there. So based on its experience, it know which movement has given its minimum distance. So it, okay, this movement has given me the minimum distance. So let me move in that direction. Again, it continues the same thing. Again, it move here and there, and based on previous experience, it can slowly move to the food or target. Okay, so this is also, there is a optimization problem where the distance is optimized. So in any machine learning problem, there is always an objective function or cost function, okay, which you are trying to maximize or minimize. Okay, there can be maximization also. Maybe you're trying to maximize the food. You're already having food, you're trying to maximize the food or something. Okay. Now, for example, we need some example. For example, we have a mountain. We have mountain. So the target right now, it is to the target right now. The problem statement is to the robot. The robot, the robot has to get down the hill. So different options are there. You can go from this option, can go for this option, this option, this option. So the robot has to reduce. For example, this hill can be considered as an error function. So robot has different options to come down and reduce the error. Or this is a mountain. It's a mountain. Okay. So robot has to choose that path or that way which is going to reduce its error to the minimum. So we'll use a differential. We call gradient descent. Gradient descent. What is gradient descent? We're trying to choose that path which is reducing my error function. So this is maximizing uh, my maximizing my gradient or difference in the error. So this is called gradient descent. So you might have heard, we'll be also using the gradient descent in neural network also to find the optimal weights. So there are a lot of options. So we have to choose that option which is reducing our error the best. So in a curve, we had to differentiate, find the differential function d by dx or d by dt of a function we call objective function or the error function. So we have to choose a way, or we choose a destination or route which is going to reduce our error or minimize our models. So this is called gradient descent example. Okay, we'll discuss more in the coming classes. And so the space, or we can see the space which we are trying to reduce, called search space. Search space. We have different space, error space, objective function space, and but usually we have solution space. We have a lot of solutions. We have a lot of solution. We have a lot of options also to reach the minimum height. So this whole the whole solution options or whole options for final destination solution called solution space. So also called search space. So space where we are trying to search the best solution, search space. Okay. Now we'll come back to our error equation. The error equation E equal to sigma. Each point I'm trying to know whether it is error or not. And target minus output of your neural network is going to add up. This is my error function. So based on this error function, we have error curve. So what is error curve? So let's see what is an error curve. So we have error curve. So something we'll draw something like this. So this is an axis. This is imagine this is a W1. This is a W2. Starting both are starting 0, so maximum 10. It's also starting from 0, maximum value 10. Now based on different values of W and W2, what I'm trying to reduce, I'm trying to reduce the error. So I am also plotting error in one here, error. This is my error plot. Okay. So this is also three-dimensional. This is a three-dimensional theorem. So different values of W and W2, I have my error. So this is okay. Now, say for example, initial we have a some kind of points here, some points there, and we already have some classification like this. So based on this error, we got error here. So this is no one right point, and all this is errors. All this was error. So our errors in last example was 14. That is 14. That is 15 minus 1. Only one right point was that rightly classified. Okay, all the so 14. So you have to mark in the W1. W1 was here. W1 was around 9. W2, sorry, W2 is 9. W1 is say for example W1 is around 8 or something. Our error was here. You know, okay, so our error was somewhat like very high error, that is 14. So I'll mark this also here, 14. 14, and I go on changing because of this error. I had to change my weights. So this is error is high. So again I change some weights. So again I put new weights, and I get a better error. I get an error of 13, and I go on like this. I go on changing the different W1, W2 options, and slowly, I'll get in one W1, W2 option. I'll get zero error. Now this is option will get zero error with this W1 and this W2. So this curve is a three-dimensional curve. Why three-dimensional curve? Because all the possibilities of W2 and all the possibilities of W1, you have some error, right? Why? Again, for understanding this, you have to go to the graphical understanding. So graphical understanding, this is your axis. So how many possibilities of line you can draw here? There are a lot of possibilities of line based on W1, W2. You can have a lot of possibilities without even considering B. I have all these options, different options of what. Say for example, W1 I have 50 options. That means, and W2 also I have 50 options. The total options of these different lines is W1 into W2. That is 2,500 different options. So again, like 2,000 different 500 different slopes here, right? And each of the W1, W2 I have B. For example, B also have 50 options. So 2,500 into 50. That means very high value. That means 125. That means this much options, including B also. So those each of this line will have its own error, right? For example, in the each of this case, for example, this line will have error 15. This line will have error again 15. This line will have error 13. This have to 12, and this has 10. This has 9. This has 8, and so on and so forth. And some at least the solution will have zero error, and there will be multiple options for solution also. This may have zero, this may have zero, so on and so forth. So if I plot all these error values with respect to your W1, W2, I'll get this error curve. Okay, so this is error curve. This is a three-dimensional curve. It has something like maybe three-dimension like this, something like this, which I'll show the different error curves. Okay, so this shape of the error curve depends upon the equation. What kind of error you are using? You can see this is a kind of discrete error we are using. T. Target is 1, output is also 1. That means true. There is no error. If target is 1, output is 0, there is an error. So this kind of discrete error here, but there are different other options also, which we'll discuss later. So now let's see based on different what are other error functions available to us. So this is the error graph. Error graph look like this. Error function we are discussing right now is looking like this. Right? This is the error function we are discussing right now. Error function equal to sigma I equal to 1 to n target minus output of your mode value. So this look like this, right? So there is some other options also. Say for example, the error function I can change to again I equal to 1 to n ti minus oi whole square, right? So I don't know what is the name of this error function, but this is also quadratic error function. Yeah, this is quadratic error function. This is quadratic error function because I'm taking square. I'm just taking square here. Quadratic error. You can see the shape. Shape is not much change, but this will be a quite slope is will much better here. I think so. Although it looks same, but you can see the maximum point is 5 in quadratic error function. Here it is maximum point is 10. Although here in our example it should be 15. Right? Why 15? because we have maximum points 15, so error can be maximum 15. All the points are misclassified, that is 15. Here it will be 15 divided by 2 because square, that is square divided by 2. 15 square is 225 divided by 2. 225 divided by 2 is something 112.5 something like. So this is based on the another example. Okay, so here there's a quadratic option is also there. So based on your problem statement, you have to decide which error function you need. So here the difference is target minus output. I'm squaring it, and I'm again taking a half. I'm using it half. For each point, I'm considering this. Okay, so like this. Now there's other options. So this is for mean square error. Means this is another widely used error function. Mean square error. Mean square error function. Right. So the equation of mean square error is based on different options of omega or w. With the mean square error is sigma I equal to 1 to n. Like in the quadratic, we are taking the target minus output square. But here I'm taking the average. Instead of 1 by 2, I'm taking average. So this is the mean square error function. And we have exponential. We have exponential error function. Exponential error function. So exponential error function is based on different values of w or weights. I have the equation e raised to 1 by tau. So this is a constant 1 by tau. Sigma I equal to 1 to n t I minus y square. The only thing is this term remains the same, but we have a multiplication with the exponential. What happens when you multiply this with the exponential and a constant? You can see the error function is changed in the graph. Error is getting a, the red means maximum error, yellow means okay, average error, green means near to solution, and this blue means very on the solution or very near to solution. So you can see the error function is changing. So based on application, you need to change the error function. Okay, so some more error function we have, this is Hellinger distance. This error function is called Hellinger distance. Hellinger distance. So what it gives you? So this equation, the equation of Hellinger distance is Hellinger distance is somewhat same, but there is some slight in 1 by root 2. So there are different scientists who makes this error function based on specific applications. Oy minus ti, you can see Oy is getting the first right now, and again the squaring is coming. Again the squaring. Okay, so this is another error function. Hellinger, it's called Hellinger's error function. I equal to 1 to n root of output of neural network minus root of target or the square, squaring. Okay, this is Hellinger distance. So another is Kullback-Leibler divergence. Kullback-Leibler divergence. So this is it. You can see the error function. Here it is. You can see quite a ridge, big ridge uses. So it's called Kullback-Leibler divergence. So how the equations? Equations is Kullback different weights. I have 1 by n sigma I equal to 1 to n t target, but log target to the output of the neuron. So this is the equation of the Kullback-Leibler divergence. Kullback-Leibler divergence. Okay, so here also there is like MSE. There's a taking an average of the error by n and taking the sum of all this t raised to I into log ti by O. Okay, just need to understand there's a different option. So you can see the error function is changing. Error function is changing in some odd way. Okay, the last two is the modified, that is generalized callback. Generalized callback. Generalized callback. Labor. Just discuss what we are discussing. Generalized callback labor. So this slight change here. So here the back labor. This is one. sorry, this is sigma. So this is sigma. I think you can just note it. I'll just share the slides. I equal to n ti log ti divided by oi. This much is similar to the Kullback. Now this is minus sigma I equal to 1 to n target I plus sigma I equal to 1 to n output this. So this is the generalized Kullback labeler divergence. Okay. The last one is Ithakura-Saito distance. Can see the distance. The graph has changed. Somewhat similar, but still it is changed. So ISD before value is omega. We have sigma I equal to 1 to n. This is Ti divided by Oi minus log Ti divided by Oi minus 1. So this is the equation for this error function. So we have different error function, and we can use different error function based on a specific application, and keep it. Okay, so I think that's from my part, and so any questions you can discuss.